page 136, section 3.2, they talk to us about graphing the derivative of a function. And so example number 1, it says the graph of the function f is given in figure 1 in blue. Sketch a graph of the derivative. And that's it. They just kind of leave me. Sketch a graph of a derivative. Great, how am I supposed to do that? So let me give you a few suggestions. These are just my suggestions of how you might want to go about this. As you do several of these, you might develop your own way that you want to go about this. But this is just an idea for starting. All right. The first thing that I do is I typically go through and I identify any horizontal tangent lines on my original function. Here's the reason for that. What is the slope of a horizontal line? 0. What's the slope of the tangent line? The same thing as derivative, right? So if I go through and I draw horizontal lines where every one of them has a slope of 0, and the slope of the tangent line is the same thing as a derivative, I just figured out where my derivative is equal to 0, right? So when I'm drawing something, like if I'm sketching a graph from scratch out of the clear blue sky, one of the things to me that's most helpful is x-intercepts, right? If I know where this graph crosses the x-axis, that's what we just found. When we found where the derivative is equal to 0, that means that when I come over here and graph the derivative in just a second, that's going to give me the zeros of the derivative. That's going to give me the zeros of the function, the x-intercepts, the roots, the solutions, whatever you want to call them. So if I go through and I say, okay, where could I draw horizontal tangent lines on this first curve? Basically, if I draw a tangent line that only touches the curve in that one spot of that one point of tangency, I want that line to be horizontal. That's basically going to occur at the relative maximums and minimums, right? So you can see I was able to draw one here and here and here. Now, rather than call that like, oh, I think that's maybe about 0.5 and that might be about 1.3, and I just labeled them A, B, and C so they'd be easy to track on the graph of my derivative. And so you'll notice over here at those same points, at A, at B, and at C, now we have x-intercepts. Okay, so that's what I know so far. Second thing that I do is I look for where my original function is increasing and decreasing. All right, look at an increasing piece for a second. So like right here, this piece between A and B, my function is going up. It's increasing, right? If you were to choose any point between A and B and draw a tangent line, okay, so like let's say I chose this point right here. If I drew a tangent line, it would look like this. If I came up here, if I drew a tangent line, it would look like this. Do you see that every one of those tangent lines is going to be going up, right? Slope of the tangent line is derivative. So if every single tangent line I draw is going up, is its slope positive or negative? Positive. And if slope of the tangent is derivative, then I just identified where my derivative is going to be positive. So anywhere my original function is increasing, my derivative is going to be positive. The opposite of that is also true. Anywhere my original function is decreasing, my derivative, or my slope of the tangent line, would be negative. Like, look at a decreasing piece. Here's a decreasing piece right here from B to C, right? So anywhere I would draw a tangent line, like if I pick this point right here, there's my tangent line, it's going down. If I pick this point right here, there's my tangent line, it's going down. It's got a negative slope. Slope of the tangent line is derivative. I've got a negative derivative there. So here's what I can do. I can say, okay, let me look at where my original function was increasing. So this piece from A to B is increasing. That means that the graph of the derivative would be positive there. And this piece from C to infinity is increasing. So that means the graph of the derivative would be positive there. Then I could go back and look at decreasing and say, okay, where was my original function decreasing? Well, from negative infinity to A it was decreasing. So my derivative should be negative there, and it is. And from B to C it was decreasing. And so my derivative should be negative there, and it is. So in essence, here's what we just created. We just made a number line where I could go through and I could say, okay, I know that from negative infinity to A, this thing is negative. I know from A to B, my derivative is positive. I know from b to c my derivative is negative, and I know from c to infinity my derivative is positive. So here's what I know, because I've got an x-intercept here and here and here. So here's what I know. I'm going to go from negative to positive through that x-intercept. I'm going to go from positive to negative through that x-intercept. I'm going to go from negative to positive through that x-intercept. I'm doing pretty good with my graph so far. Really, all I need to know then is what's going on up here. Like, I don't know how tall to make that. I don't know how high to make that go. And I need to know what's going on down here. I don't know how low to make that go. And I'm not really sure how steep to make this over here as I go off to infinity. So if I just knew that tiny bit more of information, I'd pretty much have my graph, right? And so the last thing that I do is I plot what I call strategic points. If I need to know what's going on in between A and B, I'm going to plot a point between A and B. If I need to know what's going on between B and C, I'm going to plot a point between B and C. And if I need to know what's going on as C goes off to infinity over here, I'll plot a point over there. So let's do that. Let's plot some strategic points. We said we needed to know what's going on between A and B, between B and C, and then kind of as C goes off to infinity. So in between A and B, it looked to me like an easy point to plot would be 1. So I'm going to come up here and I'm going to say, okay, let's find the slope of the tangent line at 1. Why do I want that? Slope of the tangent is the same thing as derivative, right? So I can find the value of my derivative at 1 if I find my slope of the tangent line at 1. So when I find the slope on the original function, then that's going to be the y value of my derivative. And let me show you. So we come over here and we say, okay, I want to figure out what's going on at 1. So I'm going to draw a tangent line at 1, and I'm just going to approximate that slope. It looks to me like it's pretty much rising at the same rate that it's running. So it kind of looked like a rise of 1 to 1. So a slope of 1. You might have looked at that and thought that was a slope of 1.3. It's just an approximation. It doesn't have to be perfect. It's just a sketch. Okay? So I think that looks like a slope of 1 to me at the point 1. So that means that I'm going to come over here to the point 1, and at 1, if slope of the tangent line is 1, and slope of the tangent is the same thing as derivative, then that means that at 1, my derivative is equal to 1. That literally gives me a point that I can plot there. So now I know how high to make that go. I know what kind of my relative maximum would look like. All right. Then I needed some more information between what was going on between B and C. Down here between B and C, I kind of didn't know how low to make that go. So I'm just going to pick a point in between there. I thought 2 might be a good point. So I'll go draw a tangent line at 2. So when x is equal to 2, I drew this tangent line. And to me, that kind of looked like a slope of about -2, like I'm rising about twice as much as I'm running, and it's going down. So rise of -2, run of +1. So I called that a slope of -2, just an approximation. So that means that if I come over here at x equals 2, if the slope of the tangent was -2, then the derivative is -2. So I'll come over here and I'll come down to -2, and I can plot that point. And now I know how far down to bring my graph, because I didn't know if it was kind of shallow or if it went like way down, and so that lets me have a guide. Same kind of thing over here. We said that we weren't really sure as we came out of C, does this go like straight up, or is it more flat, or kind of somewhere in between? So we're just going to do one more strategic point over there. I chose 5 as just a random strategic point over there, P. So at 5, if I drew a tangent line, it kind of looked to me, it's definitely going up, it's positive, but it kind of looked like to me that the rise was about 1.5 what the run was. So it's kind of like a rise of 3 and a run of 2 or something like that. 3 halves reduces to 1.5, however you looked at that, but that was approximately what it looked like to me. So that means that over here at point P, when x is equal to 5, then my y value would be 1.5. And so that lets me know, okay, it's not really up here or down here. It kind of gives me an idea of where to fill that in. So I can sketch the graph of the derivative from the original in that way. Now, another way that I could do that, they show us in example number 2. Example number 2 says the rate of inflation in the U.S. is a function of time. The following table gives mid-year values of this function over an 18-year period. Construct a table of values for the derivative of this function. And if you look over on the top of page 138, they literally go through and they use the definition of derivative, like f of x plus h minus f of x divided by h, the limit as h approaches 0 of that. They literally use the definition of derivative and they go through and they do it point by point by point by point for all 10 of those points. So I could do that. If I calculated the derivative at all 10 of those points, then yes, I could plot those 10 points and play dot to dot, and that would give me the graph of the derivative. I don't know that I necessarily want to calculate the derivative 10 times. I think I might prefer the method that we had used here. I think even if they gave me a table of values, I might graph that table of values. And so that graph is what you see in blue over on page 138. So once I had graphed the table of values, I could still go back and do these 3 steps that we had done right here to generate my graph instead of calculating the derivative 10 times. We're also going to look at some tools on our calculator in a few minutes that will help us as well for this type of thing. And so we'll talk about that when we get there. Okay, so look at example 3. For example number 3, they tell me if f of x is equal to x cubed minus x, find a formula for the derivative, and then compare the graph of the original with the derivative. All right, so let's calculate the derivative the same way that we've been doing. We're going to go through and use this formula, f of x plus h minus f of x divided by h. All right, so let's start with f of x plus h. That means put x plus h in the place of that x right there. So that would be x plus h cubed minus x plus h. So x plus h cubed minus x plus h. Then we're supposed to subtract our function. So let's subtract f of x. So f of x was just x cubed minus x. And then let's divide that whole thing by h. Okay, this first piece right here is so much fun. X plus h cubed. That literally means x plus h times x plus h times x plus h. So you would have to do x plus h times x plus h by FOIL and get that trinomial, and then take that trinomial times the binomial x plus h to get that cubed value. The other thing you could do is you could use Pascal's triangle from last year if you would prefer. So whichever way you want to go, when you do x plus h cubed, you're going to get x cubed plus 3x squared h plus 3x h squared plus h cubed. That's where that comes from. All right. Then we had minus x plus h, so minus x minus h. Then we had minus the quantity x cubed minus x, so minus x cubed minus a negative x would be plus x. As we've seen before with these, everything tends to start dropping out in our numerator, and that was the case here. Our x cubes canceled, our x is canceled, and then what we're left with, every single remaining piece has an h in it, so that then we can take out a common factor of h, because it was that h in the bottom that was causing us grief, right? That was what was making it to be not well behaved. So then I can cancel that h top and bottom, and what I'm left with then I can do direct substitution. So we're going to put 0 in the place of h, and so if I put 0 in for this h and 0 in for this h, then that just leaves me with 3x squared minus 1, so that would be my derivative. And I know we've done that for several days now, so we're pretty proficient with that, but that would be my derivative. So that's what they said do for A, find the derivative. Then for B, it said compare the graphs of the original function with the derivative. Using that skill set that we just got on that first problem, let's see if it could possibly make sense that if this was my original, that this genuinely could be my derivative by looking at the graph. All right, so we said number 1, look for horizontal tangent lines. So I could go through and I could say, okay, horizontal tangent line right here, horizontal tangent line right here. So that kind of looks like maybe about -1/2 and +1/2, not exactly, but approximately. I should have x-intercepts on the derivative at those same places. So sure enough, over here at about -1/2 and +1/2, I do have x-intercepts. So check that one off. Number 2, I'm going to look for increasing and decreasing, right? So I could say, okay, my function was increasing from -infinity to that first horizontal tangent line. So my derivative should be positive from -infinity to that first x-intercept. Then my function was decreasing from horizontal tangent line to horizontal tangent line. So this function, my derivative, should be negative from x-intercept to x-intercept. And then from the second horizontal tangent line to infinity, my graph was increasing, so its derivative should be positive there, and it is. I also could go back and just pick a few random points as strategic points and double check them as well, but absolutely that is the graph of the derivative of that function. I could get my calculator to tell me that too. Now, we talked before about the fact your calculator can do numeric derivatives, but it cannot do symbolic. For instance, I can't ask my calculator what's the derivative of x cubed minus x and it tell me 3x squared minus 1. It can't do that. I can say what's the derivative of x cubed minus x at 2, and it can tell me that that's 11. Because of course if this is my derivative and I plug 2 in, I'm going to get 11. It can tell me the numeric derivative, but not the derivative with symbols, with variables in it, with letters in it. It can't give me a symbolic derivative. It can, however, give me the graph of the derivative. So it can't give me 3x squared minus 1, but it can give me that graph right there. So here's how I do that. Kind of depends on whether you have the old operating system or the new operating system. So if you have an 83 with the old operating system, or if you have something that's an 84 or newer with the new operating system, this is what it would look like. All right. What I would do is I would go into y equals, and I would put in my original equation, x to the third minus x. So either way, x to the third minus x is in y1. Then in y2, I'm going to tell my calculator, take the derivative of what's in y1 at every x value. On the old operating system, when I do that, it's going to look like this. On the new operating system, when I do that, it's going to look like this. So when I put that in my calculator, I put the original, which is like the regular line, and then I set my second to bold. So you'll notice it absolutely generated the cubic as the original, and then it generated that parabola as the derivative. What I also could do then is come down here to y3, and I could type in whatever I get for my answer up here for derivative, 3x squared minus 1, and I could make sure that what I'm getting, the generated graph from the calculator of the derivative, is the same thing as the graph I'm getting from the equation that I got for derivative, right? That'd be another way to check it. Okay, so how do I put this in my calculator? Let's look at it both ways, so that whether you have the old operating system or the new operating system, you can see how to actually type that in. So I'm going to go to y equals. Let me clear out the stuff I have in here. So I'm going to go to y equals, and I'm going to put in that first equation that we had, which was x to the third minus x. All right, so x to the third minus, nope, not up there. X to the third minus x. There's my original equation. All right, then I'm going to come down here. If you have the new operating system, you can do alpha, I think it's F2. Yeah, alpha F2, and see number 3 right there is n derivative. When you hit n derivative, it doesn't go in as n derivative. It literally goes in looking like the notation that you want. So I can tell it, this first guy right here wants to know what variable I want, so I'm just going to tell it I'm working with x. And I'm going to tell it to take the derivative of what I have in y1. You could retype x to the third minus x. That'd be perfectly fine. But it's a whole lot faster to just say take the derivative of what's in y1. So alpha trace, that F4 menu, is the fast way to get to y1. And then I can come over, and right here I could tell it to find the derivative at a particular number, like 5. But I want it to find it at every number, right? So I'm just going to tell it x. All right? So one more time, the way that I did that, let me clear that whole thing out, is I went to alpha F2, number 3 there is n derivative. You also, if you hit your math button, it's also down there. If I keep going and going and going, oh, went too far, just kidding. might even be faster to scroll up to it. Yeah, it's number 8 right there. That'd be another way to get to it. So whether you do math and go to number 8, or whether you do alpha F2 and go to number 3, in either case, that's where you get the end derivative. All right, then you're going to go in and tell it, I want you to take the derivative at x, and I want you to take the derivative of what's in y1, or you could retype the equation x cubed minus x, whichever you preferred, and then tell it to evaluate it at every value of x. Okay? I like to come over here and tell it to do the first one regular and do the second one bold. So when you hit enter, it'll switch to bold. And I'm going to do a zoom 4. And so there's the original. And it's slow on the derivative because it's calculating it point by point. Okay? If you have the old operating system, you're going to put the equation in y1 that same way, but you're going to come down here to y2. Let me clear this out. You're going to come down here to y2. Hang on just a second. You'll come down here to y2, and when you go to math and you go down to number 8 and you get end derivative, it literally will just leave it end derivative. Okay? So you're going to tell it the equation, which our equation is still just y1, but the way you'll get y1 is you'll do variables, y variables, function, y1, and then you'll tell it comma the variable that you want it to use, and then comma, and typically here you would tell it the number that you want it to evaluate it at, like take the derivative at 5. Since I don't want it to do it just at one value, I want it to do it everywhere, then I'm going to put an x in there. And again, I could go over and tell it to do that second equation bold so that we could see it better. And so again, it'll graph the original and slowly but surely graph the derivative. Okay, so I put those screenshots in your notes for you so that if you're looking at this later on and you're trying to remember how to do that, that you've got it. So here's the old operating system down here, but for the new operating system, when you hit end derivative, it doesn't show up looking like end derivative. It literally goes in looking like this. And then on the old operating system, we talked about how to get y1. On the new operating system, how to get y1, and then x for x. Okay? All right, look at another one. Example 4. Example number 4 says, if f of x is equal to the square root of x minus 1, find the derivative and state the domain, and then look at the graphs. Okay? So I'm going to find the derivative. We've done this same problem before. So I didn't write out the whole derivative, but they do write it out there in your textbook if you want to see that derivative written out there on page 139. But at this point, our focus is not finding the derivative. I know you know how to do that. But the next thing it says is find the domain of the derivative. That's the first time we've had to do that. How am I supposed to find the domain of the derivative? You find the domain of the derivative the same way you find the domain of any other function on the face of the earth. Your domain is all real numbers unless one of two things happens. You get a 0 in the denominator or a negative under an even indexed radical, right? So all you have to do is once you take the derivative, just look at it. And once you look at it, you can say, okay, is there anywhere I'll get 0 in the denominator? Well, yeah, right here I'm going to have to watch out for 0 in the denominator. And I'm also going to have to look out for a negative under the radical. So I'm going to say what's underneath that radical, x minus 1, can't be negative. So typically I would say greater than or equal to 0, but because it's in the denominator, it can't equal 0, right? I'm just going to say greater than 0. And so I would solve that, and there's my interval notation for my domain. So same way I would do anything else. But let's throw that graphing component in that we've been looking at today. So let's say that I got this for my derivative and I just wanted to real quick check it. I could put this in y1, and I could put this in y2, and I could look at those two graphs and see, does that look like that could be the derivative of that? Well, let's check our 3 things. Number 1, we typically identify horizontal tangent lines. And I don't have any horizontal tangent lines over here. Well, that's a good thing because I don't have any x-intercepts over here either. So that actually is a check, right? I mean, if I don't have horizontal tangent lines over here and I don't have x-intercepts over here, that's saying the same thing. Second thing is I could look for increasing and decreasing. This entire function is increasing. So this entire derivative better be positive, and it is. And so since I didn't really have much else to go by, I might want to go through and do a couple of strategic points. So I just kind of picked 2 points. Like I said, at 1.2, I drew a tangent line there, and that kind of looked to be a slope of 2. And so over here, you can see that at 1.2, I was up here at 2, so that's good. And then I picked another point, like over here at x is equal to 2, I drew a tangent line, and that looked to be about a positive 1/2. So over here at positive 2, I should be at a y value of 1/2, and I am, so that looks good as well. I also could check this on my calculator, where I could say, okay, if I put the original function in y1, and whichever operating system you have, you put the derivative in y2, you could look and see when it graphs the derivative, is it graphing the same thing as when I graphed the answer that I got algebraically for my derivative, 1 over 2 square roots of x minus 1. If my calculator can graph the derivative for me, then let's think about a table problem, okay? If they give me a table of values and it's got 15 different values in it, and we were saying, man, I'd have to calculate the derivative at all 15 of those points and plot those points. Or I'd have to graph that all 15 of those points and connect that curve and then do these 3 steps. I could do that. Or I could put those 15 points in list 1 and list 2 and get my calculator to create a scatter plot, right? We've already done that several times this year. And then I could do a regression. Like if the stuff looks like it's cubic or exponential or logarithmic or trigonometric, whatever the graph looks like, I could do a regression and get my calculator to create an equation to fit that data, right? And then once it has an equation in y1, I can do the happy m derivative of what's in y1, and it would graph the derivative for me, right? So again, all kinds of options here that are really cool to think about with that idea that my calculator can graph the derivative even though it doesn't do the symbolic derivative. Okay, so here is our homework for tonight. On pages 144 to 146, we are doing 1, 4, 5, 7, 14, 15, 17, 21, challenge 29.